By now, you should be reasonably fluent with adding or subtracting or even multiplying and dividing complex numbers. What we're going to investigate next is one of the interesting properties of complex numbers when we multiply and divide them. But to do that, we're going to need to have the terminology to describe a couple of extra features about our complex numbers. These are called the modulus and the argument, and we're going to get into each of them in turn. We'll start with the modulus. To begin with, we need to remember that a complex number, which is essentially a number that's built from a real component and an imaginary component, can be represented on a two-dimensional plane, just like an ordinary XY graph. The graph is known as an Argand diagram, so instead of having an X and a Y axis, it has a real and an imaginary axis, but it looks the same, we can work with it in the same way, and all of the intuition that we've built up for points in two-dimensional space and for vectors in 2D space, all of that still applies to complex numbers when we think of them as points in 2D space. So for instance, this one is the complex number -4 plus 3i. So it has a real component, which is -4. It's 4 places to the left of 0, just like the number -4, but it also has an imaginary component. And the fact that it's got a real component and an imaginary component is what makes it a complex number. Technically, complex numbers include all real numbers and all purely imaginary numbers. You just have one or other of your components being 0, and that's fine. Even the number 0 can be thought of as a complex number, 0 plus 0i. But this particular complex number, -4 plus 3i, can be thought of as either the point with coordinates -4, 3, or as a vector, -4, 3. Like a column vector where the -4 tells you to move to the left 4 and the 3 tells you to move up 3. So we have a real axis, which is the horizontal line, just like we would normally draw the real line or the real number line. We think of that as being our number line, and then perpendicular to that we have this new dimension, the imaginary number line, and if we have a complex number we can treat it as a combination of those two. Now this particular number can be represented in a couple of different ways. The most sensible way that you've come across so far, the logical starting point, is to think of it in terms of its real part and its imaginary part. But there is another way to look at it. To get a sense of what I'm approaching, have a go on a diagram that looks like this one. See if you can represent the following 4 complex numbers on the same Argand diagram. 4 plus 3i, -5, -3 plus 4i, and 5i. When you've plotted them all on the same Argand diagram, you want to ask yourself, what is the common feature? What do they all have in common? What is it that makes these somehow equivalent to each other in some sense? The thing that they all have in common is the thing we're going to be measuring. Once you've had a go at that, you should be able to tackle the questions from your core pure book, chapter 1, exercise 2a. You don't necessarily have to try all the questions, but you should certainly try enough that you can build a sense of how the Argand diagram helps us to become confident representing complex numbers, and you will start to recognize some of the features of how complex numbers behave when you add them together. When you plot 2 complex numbers and their sum on an Argand diagram, you'll be able to see the similarities and the connections with vectors. Next, we're going to pick out that common feature that hopefully you spotted with all of the complex numbers you looked at before. That common feature was somehow a measure of the size of the complex number. A good way to think of size in this context is how far away the point is on the Argand diagram from the origin, the point 0, 0, or the complex number 0 plus 0i. The other thing I want to look at here is the fact that these numbers in some sense all feel like they're different, but in another sense they all feel like kind of the same. In other words, they're the same size, but they're not the same number. You've come across this before with negative numbers. The idea that -5 is the same size as 5, and yet it's not the same number. Well, in that case, it's not too much of a problem. We can put them in order. We can say that the negative numbers are going in the opposite direction. So -5 is in some sense below 5, and that's fine. But Although this works with other numbers, with integers, positive and negative, with real numbers, it doesn't necessarily work in quite the same way with complex numbers. Give it a go for yourself. Have a think about these complex numbers, the ones that you've just seen on the Argand diagram, and think about what criteria you would use to put them in some sort of order. They're not the same. And if they're not equal, then it feels like it should be possible to put them in order from smallest to largest, or from lowest to highest if you prefer. When you've had a little think and you've tried it out, unpause and continue the video. If you want a slightly more sophisticated approach to this, or you want to work on it a bit further, then you might find these four little axioms useful. Generally speaking, when we talk about a set having a natural ordering, we're usually talking about something like these conditions. If you read them through, you'll think, yeah, that kind of makes sense. That seems obvious. Trichotomy is a fancy way of saying either your number is less than my number, or it's bigger than my number, or it is my number. And that's so obvious that we never state it for real numbers. But is it something that we can necessarily say for complex numbers? Associativity is the idea that if you make more money than Bob, and Bob makes more money than Dave, then you make more money than Dave. And so obviously that works with money, it works with real numbers. Does it also work with complex numbers? I've called this next one additivity. If you have an inequality involving complex numbers, is it true that you can add anything you like to both sides and have the inequality preserved? And then the last one, a little trickier, but if you multiply two numbers that are in some order by a positive value, then is the order of those two numbers preserved? 3 is less than 7. If I double them both, 6 is still less than 14. Is that true for any number? It seems to be true for real numbers. Is it true for complex numbers? Right, if you've had a go at that and you've tried playing with the idea of putting them in order, you'll find that there's no sensible way of ordering them that preserves all of the features that we like about how we put real numbers in order. You might have come up with your own way of doing it, and there are ways of doing it, but not necessarily in ways that will preserve the things that we want to be preserved. Something will break along the way. Here are your numbers though. What they have in common is their size. So all of those numbers you've got represented there, they are all the same distance from the origin. Just like the number 5 and the number -5, the number 5i is just 5 away from 0. And the number 4 plus 3i is also 5 units away from 0. You can verify that using Pythagoras, just like you would with a vector or finding the distance between 2 points. And we give that a name. That's what we call the modulus. You might remember the modulus function from A-level maths, where we can put a number in, be it positive or negative, and out pops the size of the number. So if it's negative, we ignore the sign. Well, this is the same kind of idea, but it's a little more complicated to find the size of a complex number, because it's not just pointing forwards or backwards. It could be pointing in any one of the different directions that a two-dimensional space will allow it. Like we said though, you can use Pythagoras. So if you've got a complex number a plus bi, and you want to find the size of that complex number, the magnitude of it, as we would use that, the word magnitude we would use for vectors, we use the word modulus for a complex number because it's essentially a number, so we're thinking modulus function type thing. And the calculation you do is the same, the square root of the real component squared plus the imaginary component squared. You'll notice we're just using the coefficient of I. So a and b are real numbers in this context. Whenever you see a plus bi, it's implied that a and b are real numbers. And the only imaginary part within that will be the I itself. Any imaginary number you have, any purely imaginary number, can be written as a real number multiplied by I. And any complex number can be written as a real part plus something real multiplied by I. Next, we have a few questions to try. See if you can find the modulus of 7 plus 24i minus 4i. Can you find the modulus of z when z, complex number z, is 1 minus I? It's worth mentioning here, in case you've not come across it yet, Generally speaking, if we're talking about real numbers, we often use x to represent our unknown or the variable that we're interested in. When we're dealing with complex numbers, z is a more common choice, just because it alerts the reader to the fact that we're now working within the complex domain. A couple more, bit more algebraic in here. You'll have to do a bit of working backwards or a bit more algebra to get to your answers. See if you can find a complex number which satisfies this condition. And then a little more complicated still for part G. A bit of a bonus question for if you finish all of those. You can pause the video, have a go at these questions, and when you're done, you can check back and see the answers. So for the first one, 7 squared add 24 squared square rooted gives 25. It's one of the lesser known Pythagorean triples, 7, 24, 25. For part B, this one's easier than it looks. You don't have to think of it as 0 squared add negative 4 squared square rooted. You can just visualize it on an Argand diagram, and you can see that it's pointing directly downwards, vertically downwards. So however big the number is in front of I, that's how big the complex number is. The next one, the notation is just slightly different, but we're still doing the same thing. So we're going to do 1 squared and we'll add negative 1 squared. The square of negative 1 is 1, so you have 1 add 1, and when you've got your answer, you square root it. For the next one, you can do this algebraically, where you might notice a slight simplification. This complex number, 3p minus 4pi, is exactly p multiplied by the complex number 3 minus 4i. And it turns out, if you find the size of a complex number, and then you multiply that complex number by something, and get the size of that new complex number, it's been scaled up by exactly the same thing. Just like the way vectors work. If you have the vector 3, 4, and then another vector 6, 8, the second vector is twice the length of the first vector. You can do similar things with the next one, or you can just crunch it out algebraically and get a bunch of a squareds that combine and simplify. We should get here that a has to be equal to 7, because if you have 1 plus 2i, that has a magnitude or a modulus of root 5. If you've been looking for a complex number with a negative modulus, you will have failed to find one, because the size of a complex number, defined as the distance from the origin, can never be negative. However, it can be 0. So given that we're looking for a less than or equal to 0, we can solve this. The only value that works is the number 0. You could write it as 0 plus 0i if you like, but it's a complex number even if you write it as 0. And the last one, can you find complex numbers such that the sum of the moduli is the same as the modulus of the sum? For this one, you could have all sorts of different answers, but drawing the graph is the best way to make sense of this. The suggestion underneath in purple, sketch a couple of complex numbers and their sum on the same Argand diagram, or look back at some of the ones that you've done from exercise 2a, like in questions 2 and 3, and have a think about what the relationship is between the two complex numbers and their sum when represented on an Argand diagram. And what does it mean to say that the distance from the origin of the sum is the same as the two distances combined? Turns out what you need is for the two complex numbers to be scalar multiples of one another, or real multiples of one another, if you like. So I've put that any w which is equal to k times z, where k is a real number. So if you were to make, in fact, we'd have to be a bit more specific. K is not just a real number. K has got to be a positive real number. 0 would work as well, I suppose, technically, because then you wouldn't be adding anything, so it would trivially be true. But if k is a positive number, then when you add the two complex numbers, it's equivalent to following both of the vector instructions one after the other. And because you don't change your direction as you move along, the total distance is equivalent to the sum of the two distances. The next thing to look at is this second key word, argument. The argument of a complex number is a measure of its direction. If you're following along with the idea of a complex number being a vector, hopefully this makes sense to you. If we're going to talk about complex numbers as vectors, well, the definition of a vector is a magnitude in a given direction. You need both things, magnitude and direction. And if all you've got is the size, That doesn't uniquely specify your vector, and it's the same with complex numbers. You can have a complex number of size 5, but that doesn't tell you what the complex number is. There's an infinite number of possibilities still. If, however, we can measure the direction it's pointing, then we can narrow it down and we can uniquely describe any complex number. It's equivalent to telling you how far away a landmark is and telling you what compass bearing you need to follow to get there. We measure slightly differently. With a compass bearing, typically you measure clockwise from north. With a complex number, we use the more traditional mathematical method of measuring anti-clockwise, and we measure anti-clockwise from the x-axis, or in this case from the positive real line. If you think back to real numbers, you might have come across the phrase directed numbers when you first started learning about negatives, for instance. Real numbers can have a direction, but generally it's pretty straightforward. It's either forwards or backwards, up or down, that kind of thing. Now we've got complex numbers, things get a bit more complicated because they could point in any possible direction within 2 dimensions. So that's why we need an angle to describe it completely. It's not a case of just forwards or backwards, it's anything in between. For instance, this particular complex number, 3 plus 3i, it's not pointing perfectly forwards or perfectly upwards, it's somewhere in between. And if we measure the size of the angle anti-clockwise from the positive real line, that looks like a 45-degree angle. We could verify that. We could do a little bit of trigonometry here. If you've got an opposite side of length 3 and an adjacent side of length 3 in that right angle triangle, then you can verify that the angle is going to be inverse tan of 3 over 3. So we get 45 degrees. The inverse tan rule will generally help you define the angle, but it's not necessarily enough on its own, as you'll see when you start looking at angles in other quadrants. But when the real and imaginary components are both positive, that'll work just fine. The other thing to mention here is that the angle is usually given in radians. You will never see the argument of a complex number quoted in degrees, because everything that we do with calculus, we need angles to be measured in radians, and complex numbers are another element of higher level mathematics. If you're doing maths, the natural unit to be in is radians. So an argument is given in radians. The other thing you want to be aware of with arguments is that they will, by convention, be given within the range minus pi to pi. And if you think about it, if you're measuring an angle of minus pi, then you're turning clockwise pi radians. You're doing a half turn clockwise. That's equivalent to turning a half turn anti-clockwise. So we don't include the minus pi. Instead, we include pi. If you've got a number like minus 3i, then that's going to have an argument of pi rather than minus pi. Technically, minus pi is a valid argument, but it's not what we'd call the principal argument. An argument of 3 pi would also work okay. If you have an argument of pi, that's equivalent to an argument of 3 pi. But generally, if you're quoting the argument, you would quote the principal argument, which would be an angle between minus pi and pi. Here's another example. This one is the complex number minus root 3 plus I. And you can see already what I was talking about when it comes to calculating that angle. If you want to find the anti-clockwise angle from the positive real line, then it might be helpful to use right angle trigonometry, to use inverse tan, but it's not going to tell you the whole story. In this case, if you use inverse tan with the opposite side of length 1 and the adjacent side of length root 3, that'll tell you the size of the acute angle between the vector that's been drawn and the negative x-axis, or the negative real line. You would have to subtract that angle from pi to get the argument. Here's another one. With this one, the real component is 2 and the imaginary component is minus 2 root 3. And you can use inverse tan on that again, but the best way to do this is to sketch a quick diagram so that you can see which quadrant you're going to be in, and then you know where you're supposed to be when you're calculating your argument. So it's worth making a note. Inverse tan is a useful way to find an angle that's related to the argument, but if you only use inverse tan of imaginary component divided by real component, you will sometimes find yourself being off by pi radians. You'll be getting an answer of, let's say, 2 pi by 3, when what you really need is an answer of minus pi by 3, for instance. Might be worth investigating a little bit. Think about the conditions under which inverse tan gives you the result you want and the conditions under which it doesn't. When you've done that, you should be able to tackle the questions from the Core Pure Book 1 Exercise 2B. Those will involve finding the modulus and finding the argument of various complex numbers, and some of the more sophisticated problems towards the end will ask you some slightly different things. You'll need to do some working forwards and backwards. You'll get plenty of practice with it. When you're finished with that, come back and we'll move on to the next section, which is rewriting a complex number using the modulus and the argument instead of the real component and the imaginary component. So what we've been using so far is something that's often referred to as the rectangular form of a complex number. If you were to draw a rectangle with its with one corner at the origin and the opposite corner at your complex number, then the width and the height of your rectangle would be A and B, the real and imaginary components of your complex number. And that's a perfectly sensible format to use when we begin. We can add or subtract complex numbers in this form really easily. If you've got 2 plus 2i and you want to add it to root 3 minus I, well, you can add the real components, 2 plus root 3. You can add the imaginary components, 2i, add negative I, and that gives you just 1i. And that's really quick and simple. But it's not quite so straightforward when we're doing multiplication or division. To remind yourselves how that works, I'd encourage you to have a go at this one. You need to calculate z times w, so multiply those two complex numbers together and write them in the required form, a plus bi. Once you've done that, we're going to be investigating what happens when we look at the modulus and the argument of all the numbers involved to see if there is a nicer way of dealing with those sorts of problems. So here's what you should have got. If you multiply those out, you need to be a little bit careful here, but if you do 2 times root 3, you get the 2 root 3. The other real part comes from the final term from each bracket, 2i times minus I. That gives you minus 2i squared, but of course I squared simplifies to negative 1. So you've got minus 2 times minus 1, and that's where the plus 2 comes from. The imaginary components come from the middle terms, so 2i times root 3, there's the 2 root 3 times I, and then 2 times minus I, and that's where the minus 2 comes from. The next thing I'd like you to do is calculate the modulus and the argument of these three complex numbers, 2 plus 2i, root 3 minus I, and the result of multiplying those two, which is now written above. When you've calculated all of those things and written them in exact form, see what you notice. Pause the video, complete that, and when you're ready, come back. So here's what I've got. If z is 2 plus 2i, I can square both of those. 2 squared add 2 squared, square root the answer, I get 2 root 2. The argument I can find just by doing inverse tan of 2 over 2, because in this case, the number is in the top right quadrant, the first quadrant of the Argand diagram. But if in doubt, I can draw it out for myself and confirm that the angle I'm calculating is the angle I need. For the next one, root 3 minus I. This one has a modulus of 2. We can square the components, add them, and square root. And the argument is minus pi by 6. This one's in the fourth quadrant. So we know we're going to need an acute negative argument. And now this is what happens when we multiply the two together. We find a modulus of 4 root 2 and an argument of pi by 12. If you've not yet recognized the pattern, look closely at these and see if you can see something that's going on between them. You might have some conjectures about how these things might combine, and then if you test out your conjectures, see if they're borne out by this example. Hopefully what we've noticed is this. When you multiply two complex numbers, the modulus of their product turns out to be the same as the product of their moduli. In other words, When you multiply complex numbers, you can multiply the moduli of those complex numbers together, and that will give you the modulus of the complex number you're getting. The argument works a little bit differently. If you multiply z and w together, the argument of the resulting product is the sum of the arguments of the two original numbers. So somehow, the direction that those are pointing, they get combined by adding. Now, we can talk a little bit more about this later in the bonus section, but for now, all I'm going to say is if you think about what happens when you multiply by I, that'll make a bit more sense to you. When you multiply a number by I, it turns 90 degrees. Pi by 2, it rotates the number by 90 degrees anti-clockwise. If you multiply by I again, it moves it again. So there's something to do with rotation that's happening when we multiply by complex numbers. Good question to ask yourself at this point, if you can pause and have a think. When you multiply complex numbers, you multiply the moduli and you add the arguments. That certainly works for this example. Can you come up with any examples where it doesn't work or doesn't work in the way that you feel like it should? Are there any edge cases or examples you can find where this rule breaks? And if not, can you justify why? You'll be pleased to hear that we have a similar result for division. In fact, we don't need to go through the process of dividing a pair of complex numbers to demonstrate this, because essentially we can rearrange the results we've got for multiplication and outpop equivalent results for division. If you divide two complex numbers, the modulus of the result is equivalent to what you get when you divide the moduli of the original complex numbers. And if you want the argument of a quotient of two complex numbers, you subtract the argument of the denominator from the argument of the numerator. So we've got this connection between the size of the numbers that fits what you would naturally expect. If you multiply a number of size 3 by a number of size 5, you would expect to get a number of size 15. That absolutely works with real numbers. Minus 3 times 5 gives you minus 15. It's the right size. The direction has been affected by the negative, that's all. And it works with complex numbers. The argument is a little more interesting, and you might already be noticing some similarities between the rules that we've got here for the arguments and other laws that you've seen for some other mathematical function in the recent past. I'm not going to say much more about it, but there is certainly some strong underlying connections between the modulus and the argument version of a complex number and other mathematical structures that we've seen, because there's clearly links between multiplying and adding and links between dividing and subtracting that are going to come in useful at a later date. Let's try an example. It is perfectly possible to rewrite this number in the rectangular form, a plus bi. We need to multiply the top and the bottom by the complex conjugate, 5 plus 5i, and that will allow us to turn the denominator into a real number and simplify the whole thing. However, it saves us quite a bit of time if we recognize that we can easily identify the modulus and the argument for the numerator and for the denominator. Therefore, we can just take advantage of these laws that we've got. The modulus, all we need to do is find the size of the top and the size of the bottom and divide those numbers. 2i is an obvious one. If you think about the Argand diagram, it's pointing straight up and it goes up 2 units, so the size is 2. 5 minus 5i is a classic right-angled isosceles triangle, so it's going to have a root 2 involved somewhere. And if need be, you can use Pythagoras directly and calculate it. Even with a calculator, it'll give you a nice exact result. All I've done in the final step is rationalize the denominator by multiplying top and bottom by root 2 and then simplifying by dividing top and bottom by 2. Equivalently, you could say I've divided the top and bottom by root 2. For the argument, we've got to be a little bit more careful. It's easy to write this incorrectly. We need to make sure that when we find the argument of a fraction, we're finding the difference between the argument of the numerator and the argument of the denominator, but in the correct order. So arg of the numerator minus arg of denominator. Now 2i, like we said, is an easy one to visualize, and I'd recommend you get into the habit of visualizing these things. 2i is going to sit somewhere on the vertical axis, the imaginary axis, which means that the argument is going to be the anti-clockwise angle that takes you from the x-axis to the y-axis, essentially. That's 90 degrees, pi by 2. For 5 minus 5i, we can visualize that as well. We go along 5 and we go down 5, so we've got a complex number that's somewhere like that. If we draw in the vector and then we think about the angle we turn, you can see that's going to be a 45-degree angle, but it's below the real line, below the x-axis, which means we're dealing with a minus pi by 4. If we subtract the arguments, pi by 2, take away minus pi by 4, we get 3 pi by 4, which incidentally is the difference between the two directions of the complex numbers. If you were facing in the direction of 5 minus 5i, and you had to turn so that you were facing in the direction of 2i, you would have to turn 3 pi by 4 radians anti-clockwise. So a positive 3 pi by 4. Just a couple of things to be aware of. The division rule will only break when division breaks. So you can't find the modulus of z over w if z over w doesn't exist. And the only time mod z over mod w breaks is if mod w is 0. That only happens when w is 0 because it's the only complex number with a size of 0. So if z over w is defined at all, then you can find the modulus of it, and mod z over mod w will exist and will be equal to that. The only other minor thing to mention here is what sometimes happens when you apply the addition or subtraction rule for arguments. We still get a valid argument, but it won't necessarily fit the range minus pi to pi. So depending on what you're going to use it for, that might be fine. You know that you're going to get the same answer if you do sine of 3 pi as you do if you do sine of pi. But if it's your final answer, if it's the finished step of a problem and you're going to say therefore the argument is, it's conventional to use the principal argument. So you might need to do some adjustments. If you are multiplying two complex numbers and one of them has an argument of 3 pi by 4 and the other one has an argument of 3 pi by 4, you're going to end up with a combined argument of 3 pi by 2, which is 270 degrees. It's more than a half turn, so you would actually rewrite that as minus pi by 2. Think of it as 90 degrees clockwise instead of 270 anti-clockwise. Next I'm going to look at is a different way to write complex numbers. This particular approach to writing complex numbers allows us to leverage the whole idea behind modulus and argument making multiplication and division easier. If they're so helpful, maybe we don't ever need to find out the real and imaginary components of a complex number. They might be handy for adding, but if what we're doing with them is lots of multiplying and dividing, it will be nice if we can just describe the complex number using those two things. And they are completely sufficient for describing a complex number. Just like for a vector, I can give you the vector in column form, or I can give you the vector in terms of its magnitude and its direction, and that will uniquely define the vector just as well as giving it in a column form. So if we have a complex number z, which could be written as a plus bi, where a and b are the real and imaginary components respectively, then we're going to give some names to the modulus and the argument. We'll call the modulus r and the argument theta. And then we can draw this diagram. The same complex number can be represented in two different ways. One of the ways is to think about how far along and how far up you go to get there. The other one is to think about how far away and at what angle you need to be. But we can link these two together. We can combine them quite easily. It's a right-angled triangle. We can do a little bit of right-angled trigonometry, or if you're thinking of this more like a mechanics question, imagine you are resolving the r vector in the direction of b. So you want to know the vertical component of r, you would do r sine theta. You want to know the horizontal component, you do r cos theta. It's known as a projection. So if you project that vector down onto the x-axis, then what you get is a length which is equal to r times cos theta. However you want to do it, you'll end up with these two. R cos theta is equal to a, equivalent to saying cos theta equals a over r if you've done it as cos theta equals adjacent over hypotenuse, and we get r sine theta equals b, a direct link between those two. At this point, If you squared both of those, r squared cos squared theta equals a squared and r squared sine squared theta equals b squared, you would see that you can combine them, because cos squared add sine squared equals 1, and it would end up telling you that r squared is equal to a squared add b squared. So that fits with what we were saying about the modulus. And we can also divide them and see that tan theta is equivalent to b over a, which is not necessarily the same as saying theta is equal to inverse tan b over a, but tan of the angle will be b over a, even if the inverse function doesn't always give you the same answer. But what we can do with these as well is just rewrite a plus bi. All we're doing here, nothing particularly sophisticated. We're replacing a with r cos theta, we're replacing b with r sine theta, and now we've essentially got a way of writing our complex number that doesn't require us to know a and b. If we know r and theta, we can just write them in here. Generally, it's written more like this. We can pull out r as a common factor, and so that we don't get confused with theta times I, is that in the sine function or not, we usually put I in front of sine theta. So get used to this particular format. Z equals r multiplied by, in a bracket, cos theta plus I sine theta. This also means that if the size of a complex number happens to be 1, you can just think of it as cos theta plus I sine theta. And that can be really helpful for all sorts of things. That is known as the modulus argument form of a complex number. There are other ways to think of the modulus argument form, but they all have the same thing in common. All you need is the modulus and the argument. You don't need the real component and the imaginary component. But it doesn't have to be an either-or. When you're dealing with complex numbers, these are just two different formats, if you like, two different representations of the complex number. And just like you can complete the square with a quadratic, or you can factorize it, or you can write it in its expanded form, you can move between those different forms, and you can move between these different forms pretty easily. If you can find the modulus of a complex number and you can find the argument, like we've been working on so far, then you can convert from rectangular form to mod-arg form, modulus argument form. All you need to recognize is that you're going to put the modulus in front of the brackets, and you'll have a cos of the argument plus I sine of the argument. And of course you can go backwards the other way, because you just have to expand your brackets. If we had 3 lots of cos pi by 2 plus I sine pi by 2, well, the real bit is 3 times cos pi by 2, and the imaginary bit is going to be 3 times sine pi by 2. You should be able to have a go at exercise 2c now, which involves a bit of practice converting between the different forms, getting familiar, recognizing what it looks like when a complex number is written in the modulus argument form, and seeing how you can use them and combine them with one another nicely and quickly and easily through multiplication and division. This last section is not strictly necessary, but if you're feeling a little uncertain about how we jumped from here's a single example to this will always work, this is where I'm going to go into the detail behind that. So if what you've seen already was sufficient, then feel free to stop at this point, come back to this at a later date when you review the topic perhaps. But we're going to get stuck into this initially algebraically, and then I'm going to show you a slightly more vague but more intuitive way of thinking of it. We know that multiplying numbers in modulus argument form is really straightforward because of those rules. We're going to see if we can make sense of why the rules work. To do that, I'm going to define a couple of complex numbers, z1 and z2. The first one has got a modulus of r1 and an argument of theta1, and the second one's got a modulus of r2 and an argument of theta2. Now I'm just going to multiply them together and see what happens. If I multiply them, I multiply the two complex numbers. Writing them in mod-arg form allows us to see what's happening to the modulus and the argument. You can do a similar proof with A, B, C, and D perhaps, but it's a lot harder to tease out the information you need from that. Whereas in this form, it all falls out in a couple of lines. It's quite nice. Well, to start with, we've got 4 factors here. R1, cos theta 1 plus I sine theta 1 is the second factor. And then we've got R2, the third factor, and then that last bracket, the fourth factor. We can multiply those 4 in any order we like. So the first thing I'm going to do is multiply R1 and R2 together. That just gives me R1, R2. And then the next thing is to expand the 2 brackets. We've got 2 binomial terms, essentially, two-term brackets. So we're going to multiply those together, and we get this nasty looking beastie. Cos theta 1 times cos theta 2 gives me one of the real bits. And then the final term, I sine theta 1 multiplied by I sine theta 2, the I times I gives I squared, which is -1. That's where the minus sign comes from, right here. And then we multiply the two signs, sine theta 1 and sine theta 2. The imaginary bits come from multiplying the last term of the first bracket with the first term of the second, and the first term of the first bracket with the last term of the second. If we put those together, we get sine of theta 1 times cos of theta 2, and cos of theta 1 times sine of theta 2. And hopefully I've waffled there for long enough that some of you might have noticed something about this line. Do you recognize the structure inside there at all? And if you think about what you're trying to get towards, that might give you a bit of a clue as well. We've got cos something else, minus sine something else. And then sine something, cos something, plus cos something, sine something. Maybe if we replace theta 1 and theta 2 with a and b, it will jump out at you even more clearly. But hopefully you can see it now as the trig addition formulae. They're in the formula book. They're not necessarily the sort of thing you will have memorized, but they're the sort of thing you ought to recognize when you spot them in the wild like this. So when you compare, you should be able to identify the first one as cos a plus b, or in this case cos of theta 1 plus theta 2. And the second bracket, the imaginary component, is going to be the sine theta 1 plus theta 2 formula. So we get this. Now if you look carefully at that, you'll see that it is in modulus argument form. It's got a number in front of a bracket, it's got a cos of something, and then I times sine of the same something. That's your clue that you're dealing with something which is perfectly in modulus argument form. The angles in the cos and the sine are the same, because they both need to be the argument, and you've got cos as the real bit and sine as the imaginary bit, with an additional multiplier at the front, which is equivalent to the modulus of your complex number. And so we're done. We've got the modulus R1, R2, and the argument is the angle inside the sine and the angle inside the cos, both of them, theta 1 plus theta 2. So it must be true. However, knowing that something is true is not the same as understanding why it is true. So we're going to try to see a little bit more of what's going on with these. And I'm not going to pretend to explain exactly why the structure is what it is, but I'm going to show you a few more fundamental examples, and hopefully you'll get a sense of why this sort of thing is not completely off the wall. It builds up from the sense of how we already understand the multiplication to work and how we understand things like square roots to work when it comes to Argand diagrams. So we'll start with this. The results for the modulus are not so crazy. All we're saying is that if you multiply these things, it's equivalent to multiplying the moduli. And we're happy with that. Like we said before, if you multiply two numbers that have a size of 3 and a size of 5 respectively, the result should have a size of 15. But adding the arguments, that's a little bit strange. So we're going to begin by thinking about multiplying just by a real number that we already know and understand, multiplying by -1. I've chosen a number with size 1 so that we're not distracted by the change in the modulus. When you multiply by a number with size 1, the size doesn't change. However, the direction might. We're multiplying by a negative, and we're going to do it on an Argand diagram so we can think of it in terms of a transformation in 2 dimensions. Think about what happens to all sorts of different numbers. If you start with a number like 3, you get an answer like -3. If you start with a complex number like 2 plus I, you get an answer like -2 minus I. That would look something like this. And you might be thinking in terms of a reflection. Certainly if all we were doing was looking at real numbers, you could think of it as a reflection in the vertical axis. But as soon as we start incorporating complex numbers, you can see that we've got a negative real bit, but also a negative imaginary bit. And it turns out you have to reflect both in the real axis and in the imaginary axis to make this work. Now, if you reflect in the real and the imaginary axes, turns out what you're doing is rotation. You can try it now. If you've got a book in front of you or a phone, something that's got a logical right way up and a right way out. So you're looking at the front of your phone, it's facing you the right way round. If you reflect it by holding it with your fingers on either side and flip it so that the top goes to the bottom and the bottom goes to the top, it should be upside down, but it should also be facing the wrong way. So you're staring at the camera on the back of it, let's say. Now if you move your fingers to the top and bottom and reflect it in a vertical line, you're now rotating it so that it turns back towards you. You can now see the screen of your phone again, but the phone is upside down. In other words, the effect of those two reflections has been equivalent to a rotation by 180 degrees. And that rotation is just a single transformation, so it seems more natural that we would think of it in terms of a rotation rather than as two reflections, even though they are equivalent. And that's going to be helpful for this next bit we look at. What happens if we multiply by I? Well, what is I? I is the square root of -1. Or one of the square roots. Negative I is another one. But if we multiply I by itself, we get an answer of -1. And that means that whatever transformation multiplying by I does, it must be a transformation that if you do it twice, it's equivalent to a 180-degree rotation. Well, multiplying by I or multiplying by -I twice needs to give you a 180-degree rotation, so apparently multiplying by I needs to turn you 90 degrees. And, as it happens, multiplying by I does seem to turn us 90 degrees. You can see it from this picture. If we take the number 3, we get 3i. So this one has gone to here. And if we take the number 3 minus 4i, which is here, and we multiply by I, we get 4 plus 3i, which is here. It is a 90-degree anti-clockwise rotation. If you're wondering why anti-clockwise instead of clockwise, well, -I does the job for clockwise. That's another number that if you multiply by it twice, you get -1. But in that case, it's because you're turning the other way. Either of those numbers, if you do it 4 times, you get back to where you started, because I to the power 4 is 1, and -I in a bracket to the power 4 is also 1. So we can think of it in these terms. If we multiply by I twice to get -1, we can think of multiplying by I as being a 90-degree anti-clockwise rotation, a pi by 2 anti-clockwise rotation. And all we're saying next is, well, we can extend this indefinitely. What about the square root of I? Half of I in a multiplicative sense will be a number that's somehow part of the way from the number 1 to the number I. That's actually a number that's about 0.7 plus 0.7i. And we can look at it in modulus argument form by noticing that the argument is pi by 4, because it's half of the way from 0 degrees turn to 90 degrees turn. So hopefully that gives you a little bit more of a sense of why multiplying seems to have an additive effect on arguments for complex numbers.